Everyone. It's been a little while since um, we had a new unit. We spent some amount of time sort of navigating the consequences of momentum and energy and how they sort of can be applied to different kinds of scenarios to do useful things for us, to answer important questions, things we need to know about how to build uh, a ramp for safety or um, to assess uh, liability in a vehicular accident. There are other kinds of motion, though, that we haven't talked about yet. So far, we've discussed almost exclusively motion in straight lines. Now, just the other day, we talked about how in the accident reconstruction assignment, we had momentum along a couple different directions. But if we sort of zoom in on the motion of the car or the motion of the truck, at any given time, they are each traveling in linear motion. The car is going north, the truck is going west. They collide, and for a second, things are a little bit different. But then after the collision, they move away from that point in different directions, sure, but the direction that each of them travels is consistent. 7 degrees just north of west or 33 degrees north of west, depending which vehicle you're talking about. That, except for the fact that we change the direction, they are traveling in linear motion. But as you know, linear motion isn't the only kind of motion. We have so far said very, very little about rotation. So here we are. And that example, the example of an object held on a string moving in a circular path. If we track the location of that object as it moves, that curve that it follows is a circular path. We'll start there, and we'll go on to consider other kinds of non-linear motion. These kinds of non-linear motion. The order in which these are presented here is not the order in which we're going to talk about them, but they're here for your reference. Now, if the lanyard were to break, the circular motion would not continue. And if I apply a force to the lanyard without holding on, or a force to the clip without holding onto the lanyard, It just moves through space. It doesn't spin. It doesn't describe that circular path anymore. Something about the presence of the lanyard and the fact, see, the lanyard's important. We can agree on that. Motion in a curved path is motion in a direction that is changing all the time. In this instant, as it rotates up, the clip is moving up. At a later instant, it's moving this way. When it is above my hand, it's moving that way, and so on. Everywhere around the circle, the direction that it's traveling changes. We know from the little bit we have said about changing direction that even if you're traveling at constant speed, if your direction changes, your velocity has changed, which means you have experienced acceleration. In order to experience acceleration, Newton's laws anyway, require that there is a force. There must be a non-zero net force in order to accelerate an object. The force that sort of permits circular motion like this, we call the centripetal force, which means towards the center. All the time, we're pulling along the string towards the center. If we just toss the clip up, in order to cause it to rotate, we have to pull down to stop the clip from going that way. We have to pull down towards our hand and cause the motion at all times to stay in circle, because the inertia of the object is going to try to move away in a straight line. It is moving this way, so it's going to continue moving that way unless we tug it back always into circular path. That tugging inward, that's centripetal force. Centripetal force is what prevents, this is maybe particularly relevant given the weather event we just had recently. If the road is wet or icy, or if the car is going too fast, the force from the road, the friction, maybe isn't strong enough to prevent the car from skidding. There needs to be a force directed inward. On a flat curve that we're driving on, it's friction that's doing that job. Somehow or other, the net force needs to account for the fact that we have to change the direction of the car. If there isn't enough net force to do that, to change the motion, the direction of the car at the speed that it's going, then it's not going to stay in a circular path and it's going to skid out of the turn. Which can feel, as you know, right? If you take a turn in a car a little bit too fast, you feel pulled to the outside of the turn. That feeling we call centrifugal force, which means going away from the center. As we turn, let's say we're turning to the left, we feel pulled to the right in the car. Notice these words, seems and apparent. As we're standing on the curb, watching a car go around a curve, there's nothing. There's no thing pushing outward. That feeling we feel is a feeling related to our own inertia. We were traveling that way. And then we want to change our motion. But our inertia wants us to keep going that way. Going that way as we turn, that's going to feel eventually like pushing out of the turn. There's no force doing that, though. It's just an expression of our own inertia. We know that. If we break the string, if we break the lanyard, it doesn't continue moving in a circle, nor does it run away from the circle. If I let go right at the instant, I'm not going to because it's going to hit the ceiling and make a dent. But if I let go right at the instant we're traveling up, the clip at the end of the lanyard is just going to travel up. It's not going to go way over there. It's not going to come back around over this way. It's just going to travel up. Because as soon as the force from the lanyard stops acting, the force on it is only gravity. So it has some speed and it's just going to go up. If you've ever been roller skating or ice skating with a group of people, and you might have played Crack the Whip. There's a line of people and someone's on the outside and everyone skates kind of around, and then the last person gets flung forward. They don't continue going around, and nor do they turn off. They just go straight tangent to the circle. How strong does centripetal force need to be to keep us in a circle? Okay, well, it might make sense. The heavier the clip, the harder it is, the more inertia it has, the harder I have to try to keep it in the circle. The faster it's going, the harder I have to try to change its, the more acceleration I need, because I need a big speed this way to change into a big speed this way, into this way, into this way. The bigger the speed, the more I have to try. It also depends on the size of the circle. That's what we mean when we talk about, when we're learning to drive, we talk about taking a turn too tightly. The larger the radius, note that it's in the denominator of this fraction. The larger the radius, the smaller the centripetal force we need. The bigger the curve in which we're going to try to turn left, the slower our acceleration can be for any given sort of amount of time, because it's going to take us longer to get from this way to that way. Mass times tangential speed. In other words, what your speedometer says as you're driving in a circle. Mass times speedometer squared divided by the radius. One extra note about centrifugal force. We don't spend a lot of time in a reference frame that is itself rotating. Imagine Imagine that this bug is in this can, and the can is at the end of a string being swung in a circle. Now, the bug can't see the outside, doesn't know that it's being swung in a circle. All it knows is that it feels pushed against the outer wall, the bottom of the can, over here, against that wall. And we know that we feel that as we're going around the turn in the car. If you close your eyes, what we feel is the door and the seat pulling us in. We feel pulled to the outside because what we're actually sensing is everything pushing inwards on us, and our own inertia is kind of trying to run away with us. In order for there to be an interaction between the bottom of the can and the bug's feet, there's got to be something holding them in contact, like gravity holds us in contact with the floor. And it's this expression of the bug's inertia because of the fact that its entire world is vibrating. Its entire world is rotating right now. The centrifugal interaction is what's pushing, what's maintaining the contact between the bug's feet and the can wall or bottom, I guess, to make that contact force. It's actually like a support force, like normal force. It's just sort of tilted. It's not gravity that's pulling us against, it's the centrifugal force. It's the expression of the bug's own inertia. We could use this effect because the bug can't really tell any difference between standing on the bottom of the can, like when the can is upright, set on the desk. Can't tell the difference between gravity making the contact between the bug's feet and the bottom of the can, or being spun in a circle, and the centrifugal force making that contact between the bug's feet and the bottom of the can. We can use the inertial effect, our own inertia, in a rotating environment to simulate the feeling of standing on the ground in gravity. This person feels a force on their feet from the floor, just like the force that they experience standing on the ground on Earth, because their whole world is rotating. And that rotation creates an interaction with the wall, the outer wall of this ring, that feels like gravity. And if we put this thing in outer space, we're not going to know the difference because we can't feel regular gravity because we're in outside the normal gravitational effect of the Earth. So we're going to feel this interaction, this circular thing, it's going to feel like gravity, and we can walk around just like we would, sideways, walk around on the wall. Eventually, we can show that this is true, but in order to simulate Earth gravity, a space station like this, a rotating space station, should have a radius of about 1 kilometer and rotate at about 1 revolution every minute. Any faster than that, and the fluids in our bodies can actually they slosh a little bit, and we can feel that we're in rotational motion. We get a little bit like seasick, a little bit motion sick. So we keep. That's why we need the radius to be so large, so that we can have a fairly slowly rotational speed. Notice that 1 revolution, 1 full circular path, once around 360 degrees, let's say, 1 revolution per minute is not the tangential speed. That's not a speedometer reading. Our cars don't talk about rotations or revolutions per minute. They talk about miles per hour, just straight line, tangential speed. This is given to us in terms of rotational speed, and they are different. I'm gonna this most of this slide. I modified this slide a little bit. Here's how I'd like us to think about this. If we're talking about the clip moving in a circular path because the point around which it is rotating is outside itself. Here's the clip, and here's the point around which it's rotating, and there's space between them. If we rotate a thing around an axis that is external to itself, that thing moves in a circle. We can trace the circular path through space of that. In contrast, fly swatter here. If let's do this. This is rotation as well. Rotational motion, right? But the thing is, it's harder to talk about the circle that this goes through, right? The clip, we can trace the circle in space. Where do you draw the circle for this? I actually have an answer for you, but we don't have it yet. That motion, if we rotate around this point here where I'm holding it, if we rotate around that point, keep that point fixed, I'll say that that's internal, because it's an axis that passes through the material of the object. The shape of the object and the axis around which we're rotating passes through the object. that actually passes through the material of this object that then rotates around that point. Is this circular motion? Yes. Is it helpful sometimes to call it just rotation? Yes. So for now, if it turns about an external axis, we can call it circular motion. If it turns about an axis that's internal to its own sort of shape, its own size, then yes, it is circular motion, but let's just call it rotation. Rotation about an axis. As we've already seen, rotational motion, whether it's circular or not, is characterized by two kinds of speed. Tangential, which is linear, that's the speedometer, and rotational, or circular speed, which is how many circles per time. How much circle per time. This is let's say it's a record on a turntable. The entire record is rotating about an axis that goes through the center of the record. The entire record rotates once every so and so many seconds. The rotational speed of the record is whatever it is. This many revolutions per minute. Maybe 45 rotations every minute. And every part of the record, if we talk about these two bugs standing on the record, each of them makes 45 rotations every minute. They're going to get dizzy. Do bugs get dizzy? Now, ignore the record. Ignore that the bugs are standing on the record. The inner bug, this one, is moving in a circle of a particular radius because it's a particular distance away from the axis. So in the amount of time that it takes the record to rotate once, this bug makes a circle in space that has a particular circumference. So we travel a particular distance in some amount of time. We have a linear, a tangential speed, a speed with which we move around in a circular path in space. The bug on the outside, in the same amount of time, right? Because the whole record is rotating. In as much time as it takes to make one full rotation, that bug is traveling a larger distance through space, has a larger tangential speed. Points further away from the axis, which is what closer to the circumference means. Points further away from the axis around which we're rotating have a greater tangential speed than points close to the center. Rotational speed is the number of rotations or revolutions per time. So how much rotation divided by how much time went by. All the parts of a turntable rotate about the axis in the same amount of time. All parts have the same rotational speed, but we multiply by the radial distance from the axis to the point we're talking about to talk about the v tangential speed. So for normal linear speed, we're going to keep the same sort of symbol we've always had, v. For rotational speed, it's a new thing, so we got to give it a new symbol. And I'd like to give it this sort of swoopy W. It's the Greek letter omega. inertia, still a thing. An object rotating about an axis tends to remain rotating that way unless something interferes with it, which sounds a lot like the first law of motion, the Newton's first law of motion. The property of an object to resist changes in its rotational motion is called rotational inertia, which is hardly a surprise. Let's use the symbol I. This is not a lowercase l, this is a capital I in this particular typeface. I for inertia. Now, the thing about that is that, yes, it depends on the mass of the object. The more massive the thing is, the more it's going to want to continue rotating the way that it is rotating. But it also depends on how that mass is distributed relative to the axis around which we're trying to get the thing to rotate. The greater the rotational inertia, the harder it is to change the rotational state. Tightrope walkers are sometimes seen carrying a very long pole because the longer the pole, the further away from them the mass is distributed. And the further away the mass is distributed, the larger the rotational inertia. The more the whole system of tightrope walker and pole resists changing its rotational state. And if we aren't rotating to begin with, it's going to try to stay that way. So it's a little bit of an effort not to tip over, because the pole is going to try not to tip over more than our body will. It is easiest to rotate a pencil, or really any long object, around an axis passing through its length. Rotating the meter stick or yardstick around the axis that goes along the stick this way is not hard at all. I mean, all I basically have to do is allow it to fall off my hand, and it'll spin that way, kind of on its own. It's harder than that to get it to rotate around a vertical axis passing through the center, or a horizontal axis passing through the center. This is a harder motion than this. And it's even harder still to create motion around a point on its end. Try this for anything heavier than a yardstick, and you'll see that this is true. The object that comes to mind is a metal baseball bat. If you grasp the bat along its length about halfway, maybe a little bit closer to a little bit farther away from the handle, it's not hard to get the bat to rotate like this. Certainly not compared to if you grab all the way at the handle end and try to get it to rotate in a big circle. One of those will be much, much harder. It's the same mess, but we are also interested in how it's distributed relative to the axis we're trying to get it to rotate around. Most sort of, Geometrically symmetric objects, we can calculate their rotational inertia. A hoop, just and I don't have a hoop handy, but yeah, just a ring, not a disc. We get different results depending how we try to rotate it. This is the picture that is like a wheel or like a hula hoop rolling along the ground. It's rotating around an axis through its middle. This is like, you know how if you flick a coin, it'll spin, but it's like doing that with a hula hoop. So just put the hula hoop on the ground and then start it to spin in place. One is a different distribution of mass relative to the axis, and so on. If we were talking about a disc instead of a hoop, we would use the solid cylinder. Note that if it's the axis through the length of the cylinder, we don't care how big the cylinder is. The length of the cylinder in the picture from here to here, because all we're doing is rotating. All we care about is how the mass is distributed relative to the center. Well, okay, so make it longer. It's still in that shape distributed around the axis. Calculating these requires calculus. So we aren't going to calculate the rotational inertia of any new shapes, but we could use these results. These are tabulated in our textbook, and we can use them to talk about the rotation of geometrically symmetric objects. Okay, so we've talked about rotational speed, and just now we've talked about rotational inertia. Now, back when we were talking about Newton's laws, inertia was mass. Like mass was the thing that talked about how much inertia we had. That's fine. Now we're talking about rotational inertia, which is the thing, at least as far as rotation goes, that tells us how much inertia we have. Mass times velocity, mass times speed used to be momentum. Mass times velocity used to be linear momentum. Instead of mass, the inertial thing for linear motion, let's think about rotational inertia. And instead of velocity, let's think about angular or rotational velocity. So we do the inertia piece times the velocity piece, and we get the momentum piece. It works for linear, and it works for rotation as well. We could talk about a rotational momentum or an angular momentum. Angular, not because we're making any sharp angles, but because as we move around, as we rotate, we sweep through angle. I mean, we talk about something undergoing 360 degrees worth of rotation. Well, that's an angle, right? So we're talking about angular motion as opposed to linear motion. For a small object, such that we can say pretty much all of it is located a distance r away from the center of the curved path. The tangential speed, tangent to the circle. The mass, that radial distance. Tangential speed, whoops. Tangential speed times radius mass. Rotational inertia looks like mass. We're talking about like a simple pendulum, just a mass a distance away. The rotational inertia is m times the radius, the mass times the radius squared. Okay, so angular momentum is rotational inertia, mass times radius squared, times angular velocity. But angular velocity, or rotational, times one of those radiuses that's in the squared, that's the tangential speed. So it's mass times radius times rotational speed, but radius times rotational speed is tangential speed, and that's where this equation comes from. An object at the end of a long string, or a planet moving around the sun, or something like that, such that the distance between them is large compared to the size, so that we can argue that all of the mass of this object is basically the same distance r away from the axis of rotation. If no net external rotational force, that's a mouthful, acts on a rotating system, then the angular momentum of that system should be constant. We're saying Newton's first law, but for rotation. If no net force acts, then the momentum, if no net linear force acts, then the linear momentum was constant. We said that a couple chapters ago. Fine. If no net angular force acts, then the angular momentum should be constant. Okay, so we can talk about conservation. If we're on a spinning table and we have these weights in our hands, if we bring our hands in, we decrease our rotational inertia because we have moved the mass of the system closer to the axis around which we're rotating. We see this when we watch, figure skating. A spinning figure skater starts the spin with arms outstretched, and then brings arms in and spins faster. This is what's happening. It's the conservation of rotational momentum. Net rotational force, let's call it torque, not TWERK. That's a different thing. Torque. How much torque we create depends on three factors: how much force we use, the direction in which the force acts, and the point at which it is applied. Now, we know this is true if what we want to do is close the door, we push on the door, we apply a force. The door doesn't move all in one go. It rotates around the hinges. So when we push on the door, we're applying torque. Well, we're applying a force, but then that force creates or sort of exerts a torque on the door to cause it to rotate. Push harder, it'll close faster. Magnitude of the force. The point on the object at which it is applied. Have you ever gone to open a door and pushed at the wrong side? Right? Like it swings, I don't know, swings this way, but you've accidentally pushed at this side and nothing happens. If I apply a force way over here at the hinge, the door barely closes at all. If I push on the wrong point on the object, the wrong radial distance from the axis around which I'm trying to get it to rotate, it's not going to rotate as much. And the direction of the force. If I want to close the door, I apply a force kind of at the door, at the plane of the door. If I don't do that, let's say I push this way into the room, it doesn't close as much. If I use the same, strength and push at the door, like really, it closes almost all the way. Magnitude of the force, its direction, and the point at which it's applied relative, again, to the axis around which we're going to rotate. So now that we have this torque, we can talk about Newton's first law for rotation. An object or a group of objects will maintain its angular momentum unless acted on by net external torque. How much torque? We need to know how much force. That's force. And we needed to know where the force is applied and the direction in which it acts. And those two pieces together are what we call the lever arm. If we want something to rotate, think about like a seesaw, right? We're going to apply a force here, which causes the seesaw to rotate. That's like the simple machine. That's like a lever. So how long, what is the effective lever arm? If we push the right way on the lever, we get the most effect for our force. But if like I did with the door, if we push at an angle, even if we're applying right at the end, we're not going to get as much rotation because we didn't get as much torque. The lever arm is less than the length of the handle of the wrench in the first picture because the force is at a weird direction. Well, weird, not perpendicular. In the second picture, we changed the direction of the force. We haven't changed its magnitude. We're still pulling on the wrench with the same force. But because we're kind of optimizing the relationship between the lever and the force that we're using to create rotation, we're going to maximize our torque. Unless we've got an extension bar for the wrench and we can make the lever arm even longer. Same amount of force is going to, because the lever arm is longer, produce a greater amount of torque even. It makes me think of, I think it's Galileo. Give me a long enough lever and a place to stand, and I can move the world. The longer the lever, the more torque we can exert. Earlier, I was talking about the fly swatter. And I said, is rotation about an axis through the center or through an axis, rotation around an axis that passes through the object, is that circular motion? And I answered yes, except we're not quite sure where the circle is. Do we draw it from the outside or from some point somewhere in between? And the answer is from some point somewhere in between. Where is the mass of the fly swatter? It's at its center of mass, and we already have bumped into center of mass. Here, now, we can talk about why the center of mass experiment that we did with the rotating, the nickels on the paper, and it rotates. Why does that work? Because the center of gravity and the center of mass for most objects are the same point. This is hardly surprising. I expect, since this object is symmetric, I expect the center of mass to be somewhere on the center line, because center of mass is the average position of all the mass of an object. If we want to talk about the rotational okay, let me try that again. If we want to talk about, the rotational motion of this object, which point should we track the circular motion of the center of mass? Where's the center of mass? It's at the center of gravity. The point at which, if I support the object there, I can hold up this entire object by applying a force right there. So that must be where the center of gravity is, which is where the center of mass is. So imagine I stuck an LED right there and then spun this around and recorded it. There would be a circular, a lit up circular path that was the path made by the center of mass. And that's why rotational motion is circular motion. It's just sometimes hard to see it. We think about that circular space station. The space station itself doesn't really move, it just turns. It's hard to think about that as circular motion. And in that case, the center of mass isn't actually in motion. So it doesn't really look like it is circular motion, but it is rotation. So that's why we talked about both. But if we wanted to talk about the circular motion of an object about an axis through the material of the object, it's the center of mass that tracks that circle for us. We know this already. To determine the center of gravity, suspend the object from a point and draw a vertical line. This has implications for the stability of an equilibrium. We've got the Leaning Tower of Pisa. It's a sort of go-to example. Galileo was there doing his air resistance thing. If we have some kind of balance, if we draw a line straight down from the center of gravity and it falls, like the line that we draw passes within the area of support, the base of the object, then we can say that this object is in a, at least locally, stable equilibrium. We can poke at the Leaning Tower of Pisa and it won't go anywhere. In contrast, if I try to balance this yardstick on its end, it will not take very much at all for a disturbance to mean that from the center of gravity, the line that we draw does not pass within the area of the end of the meter stick, and it'll fall. This, the stability problem, has implications for civil engineering, which we will explore a little bit. If you're going to drive your car around a curve, we said a minute ago that we're relying on friction to keep, to perform the centripetal task, to be the force that makes sure that the net force is what it needs to be to keep us in the circle. What if it's wet or icy? Is there a way we could design the road to help, like to mitigate the problematic effects of less friction? And what does that have to do with stability of the equilibrium, let's say, of like a fully loaded tractor trailer with mass all the way up to the roof? If that tips too much, it'll tip over. If the center of gravity falls outside the wheelbase area, it's worth a look, I think. We will explore some of these things in our upcoming activities. Thanks, everybody. See you next time.